let's look at the formula for density in case of normal distribution once again. And now you can see I rewrote it a little bit. So it's the same formula, but now you can see that I put this value x minus mu divided to sigma in a parenthesis. I didn't change anything. It's the same expression. Okay. So what it means? It means that we can simplify it by setting a new variable z or z to x minus mu divided to sigma. So instead of this x minus mu divided to sigma, I simply can use z. What it gives us? Well, first of all, apparently we create a new variable, right? So instead of x, we kind of transform x. So instead of x, we will use z. But why we do that and what kind of benefits we can get if we make this transformation? So to answer this question, let's think about the parameters of z. So we know that x is normally distributed, right? We can write it like this. It's normally distributed with parameters mu and sigma. Right? So this expression means x is normally distributed. Sometimes you can do it like this. It's normally distributed with parameters mu and sigma. But how z will be distributed? Well, if x is normally distributed, apparently z also will be normally distributed because you just make a linear transformation. You subtract something and divide something, right? So you don't change the distribution. But what will be, for example, mean and standard deviation of z? What will be mean of z? Well, let's think, right? So what is mean of z? Mean of z is, if it's a population, z1 plus z2 plus and so on and so forth plus zn capital N, right? Divided to capital N. Okay, we can do it like this. x1 minus mu divided to sigma plus x2 minus mu divided to sigma plus and so on and so forth plus xn minus mu divided to sigma and then everything divided to n. I just simply replaced this using this expression, right? Now, because in all these terms on the top, denominator is the same, it's sigma, we can rewrite it like this. x1 minus mu plus x2 minus mu plus x3 minus mu and so on and so forth plus xn minus mu divided to n sigma, right? Which is x1 plus x2 plus and so on and so forth xn divided to n sigma minus mu times n divided to n sigma. Now, what is this? This is exactly mu, right? This is exactly mu. So we'll have mu divided to sigma minus, and then you can see n cancels out, mu divided to sigma, which is equal to 0. So what it means? It means that the average of z values always 0. Regardless what mu you have, what sigma you have, what x you have, average, if you compute this transformation, if you get from x to z by subtracting mu and divided to sigma, you simply get values which always have 0 average. So now we know that average of z is 0. What will be the standard deviation of z? Well, the same idea. So let's compute it, right? So we know already that sigma, let's compute the variance. So it will be z1 minus mu of z, right? It's just to separate because this is mu of x values and this is mu of z. Then square it, right? Plus z2 and so on and so forth plus zn minus mu of z squared divided to n. But we already know that mu of z is equal to 0. We just derived it before, right? So it means that it will be the same as just simply z1 squared plus z2 squared plus zn squared divided to n, right? But now recall that z1, it's x1 minus mu divided to sigma and mu of x, right? So we can just write it like this. x1 minus mu squared divided to sigma squared plus x2 minus mu squared divided to sigma squared plus and so on and so forth, plus xn minus mu squared divided to sigma squared and divided to n. Yeah. Again, denominator is the same. You will have x1 minus mu squared plus x2 minus mu squared plus and so on and so forth plus xn minus mu squared divided to n sigma squared. But now look, let me just use another color. This part is exactly sigma squared. This is how we define sigma squared. So this will be sigma squared divided to sigma squared, or 1. So it means that the variance of z-scores is always 1. Average of z-scores is always 0. And the variance of z-scores is always 1. And therefore the standard deviation is always 1 as well. So z-values have always the same parameters. Average is always 0, and standard deviation and variance is always 1. So therefore we will call this as z as a standard score. What's the meaning of the standard score and why we use this transformation? And the meaning is actually very simple. Z-score, it's a distance. It's a measure of distance. It's a measure how far your values go from mu, but in special units. Let's look at this. What do we have in nominator? We have distance from x to mu in the same units of as x, right? So for example, if x is height of people in centimeters, this will be distance in centimeters. If x is a concentration in milligrams per liter, this will be distance in milligrams per liter, right? So this is distance. What do you have in the denominator? Well, sigma. But what is sigma? Sigma, it's how many units of x you have in one sigma, right? So when sigma is 10 centimeters, it means that 1 sigma is 10 centimeters in x, right? So 1 sigma corresponds to 10 centimeters, or 1 sigma corresponds to 5 milligrams per liter, and so on and so forth. So it's also distance. So now you measure distance in the real units, and then you divide how many of these real units you have in 1 sigma. So what it gives you how many sigmas you have in this distance. So z-score tells you how far x from mu in sigma. It's like miles in the United States. For example, if you say like this city is 160 kilometers away from another city, right? So it means nothing. But then you remember that, okay, 1 mile is approximately 1.6 kilometers. So you can recalculate this distance to miles, and then people who use miles instead of kilometers will understand this better, because you provide distance in units, which is actually they mostly used, right? So that's the same. So in normal distribution, we measure all distances in standard deviations. And z-score, it's exactly the way to compute distance in standard deviations. So z-score tells you how far a particular value is from the mu in standard deviations. That's the meaning of this. So z-score or standard score is just a distance. Now let me show you a practical example. Let's say salaries in a company ABC with 10,000 employees, so this is our population, are normally distributed. This is average salary, and this is standard deviation for the salary. Now, what can you say about these two salaries? John has a salary of 20,000 krona, and Julia has a salary of 45,000 krona. If you just look at the numbers, it's very difficult to assess it, right? So you see that John is below average and Julia is above average. You can see John is 10,000 krona below average and Julia is 15,000 krona above average. It sounds like it's the same magnitude, but just a little bit below, a little bit above. But if you calculate these distances between the salaries of John and average salary and salary of Julia and average salary in standard deviations, that will provide you additional information. For example, let's start John. So John X is 20,000, right? So if you compute z-score for John, it will be, remember, x minus mu divided to sigma, right? So it's 20,000 minus 30,000 divided to 5,000, which is, this is minus 10, this is minus 10,000, divided to 5 will be minus 2, right? And now it means that it's 2 standard deviation below the average. If you think about normal distribution, so this is normal distribution, right? So here we have 30,000, so this is the average. here you have mu plus 2 sigma, and here you have 2 minus mu minus 2 sigma, which is exactly the John's salary, right? So this is 20,000. This is John's salary. And then you know from our basic knowledge of normal distribution that here you have 95.5% of all employees have salary between these two, right? So how many outside? 4.5 outside. Half of this 4.5 is here, 2.25% here, and 2.25% here, right? So the John's salary, it's like approximately the second percentile. So only 2.25% people in this company have salary smaller than John's salary. Using z-scores and understanding the meaning of normal distribution and what sigma means for normal distribution make this comparison much, much easier. Now let's talk about the Julia's salary, right? In this case, x is equal 45,000. So z-score for Julia's salary is 45 minus 30 divided to 5,000. Yeah? This is 15 divided to 5 will be plus 3, right? Again, if you remember, this is normal distribution. So here you have average. This is average plus 3 sigma. This is average minus 3 sigma. And you know that here you have 99.7% of all values. That means that here you have 0.15%. And this is where the Julia salary is. This is exactly plus 3 sigma because this standard score is 3. So it means it's in top, very small amount of people have salary like Julia. Remember, it's 10,000 employees, right? 1% of 10,000 will be 100. And then 0.1% of 10,000 will be just 10, right? So in 0.15, it means 15 employees have salary above Julia. So he's probably a top manager and so on. So z-score allows you to understand how extreme your value is compared to the mean and for given population parameters very quickly. So that's why z-score is important. Now, of course, we can also make distribution of z-scores, right? So in this case, we have a very simplified version. You remember sigma is equal to 1 if it's z-score, and this is replaced by z. So this is the distribution of, this is how density distribution function looks in case of z-scores. So you can see very simple case. And now we know that this distribution has fixed parameters. Mu is always 0, and standard deviation is always 1. Variance is always 1. Therefore, we call this distribution a standardized normal distribution. And this is how it looks like, right? So you can see this is 0. This is 1, 2, 3, minus 1, minus 2, minus 3. And you remember, right? So what's the meaning of this one? It means 1 standard deviation away from mean, 2 standard deviations away from mean, 3 standard deviations away from mean, okay? And that gives us additional possibility. So you can see that z is equal to x minus mu divided to sigma. If we multiply both sides to sigma, you will have sigma z equal to x minus mu, right? Now, if you add mu to both sides, you will get this one. So if x is normally distributed, what it means? It means x has expected value, and also x has a variation parameter, right? How big the variability is, how far x can go from the expected value. And z, it's exactly the randomness. That makes x random. If we don't have any randomness, z equal to 0, and then x will always be equal to mu. So in ideal world where we have no randomness, x will always be a fixed value. It will be equal to mu, but because we are not living in a random world, we have this randomness parameter, and that's exactly what provides z. Z, it's a randomness. That z is what makes your x value random. And then you can see a clear correspondence between distribution of z-scores and distribution of real values, right? For example, mu for z is equal to 0, but for real values, it's equal to average of the population. It's 170 in this case, right? Then these distances, for example, if you have z-score equal to 1, what's the meaning of this? It means 1 standard deviation away from here. So here it's just 1, but here it's 1 standard deviation because you can see standard deviation is 10, and here you have 10, right? Then the same in this case. So this is just minus 1. So it's minus 1 standard deviation away from mu. But you can see this is also minus 10. Minus 10 because standard deviation is equal to 10. So z-score is just a standardized distribution, standardized normal distribution, which you can use, for example, for representing any values if you know parameters of population. In the next video, we will talk about CDF and ICDF function for normal distribution.